Sir, we are live now. Thank you.
Yes. Good evening, friends. Welcome to the institution's fourth technical webinar session of 2022. Today's session will begin with a short remembrance session in memory of our fellow naval architect, Mr. Sateesh Dev, who left this mortal world on 16th of May. We are very fortunate to have the presence of Mrs. Deepa Dev with us. We shall have a few short speeches from our fellow naval architects who knew Mr. Sateesh Dev. This session will be followed by a technical presentation from Dr. Sriram, an extremely bright young researcher from IIT Madras. He's a faculty there. That session will be chaired by Professor Vishwanath Nagarajan from IIT Kharagpur. And we are very happy to have Dr. Purnima Jalihal from NIOT as our chief guest. May I request Mr. Kocher to please initiate the remembrance session, please. Thank you.
Thank you, Mr. Dasgupta. I'll give a very brief my association with Sateesh, a very pleasant association because his two classmates are going to talk more about him. I met him first time in 1975 and at Mazagon Dock when he was started his career and he was assigned on the Jacob Rig project. I was assigned from ABS and we worked together, I think maybe for 5 years. And the management that time realized his potential and at a very young age appointed him as a kind of de facto manager for that project. And lovely association we had. We had social association with him and Deepa, and met socially at his place, our place. And then, of course, he left. This project was designers of Baker Marine. They found him so good. They took him along to Singapore. And then, of course, there's no end to it. He professionally, he excelled. He worked for Modec and a few other companies, and we all know where he reached. My contact with him was very limited after he left. But when I was in Singapore, I always inquired about Sateesh from common friends like Anis and Ravi Chadha and about his welfare and his wife's welfare. And I miss him, feel very sorry, and my deep condolence to the family. And may his soul rest in peace. Thank you.
Thank you. Thank you, Mr. Kocher.
Thank you very much. May I request Mr. Dr. Sabasati Mukherjee to kindly say a few words?
Yeah. Hello, Deepa.
Hi, Sabya.
Hi, everybody. Now, I am a 75 batch. So 1970 was the year that I first met him in IIT Kharagpur. We are in the same hall, and we are five naval architects of that batch who was there in that hall. And we are fondly called the Pandavas, 5 Pandavas. So, since then, I never lost contact with Sateesh. And it was, even in short holidays and all, he will accompany me to my family in Kolkata, and he was a part of my family then also. And it never stopped. In fact, when I was going for higher studies, and my flight was routed through Bombay, so he came over to see me off, and it was an early morning flight, so he spent the night in the transit hotel, and then he saw me off. And then after I came back, I kept constant touch with him. He was in Mazagon Dock, I was in Goa Shipyard, and we used to exchange notes and many things. He helped me in that. And then, after that, it was in Bombay, it was intermittent. But from there, when I came to Singapore, I happened to be the next door neighbor. So we used to do things together. And Deepa, Sid, and our family were very close. And even they used to buy things, like cordless phone. First time it come in the market, so we
Yeah,
each
I
one of
remember that. There was, yeah.
then we were testing it because we were staying, in front of each other's house, very close. We used to test the range from each other's house, that whether it can reach the base unit. So all these time we never lost touch, and I think that Satish feel very proud of each other. I mean, there was no professional rivalry at all. We used to feel happy at each other's, success, and that was one of my inspiration also. That Satish, I mean, he used to encourage me a lot, and his career journey had been amazing. He has, I know him when he was in Baker Marine, and since then he went to Bethlehem, Sembang Bethlehem. From there, he went to Keppel, joined Keppel, and then Modec. And also, he was not only a good careeristic, but he also had a lot of people he were mentoring. And there are a lot of people who will vouch in his name that he has helped them a lot. So, other than that, so far as last time I saw him, when he invited me to Delhi for his, he was a very proud father. He was very proud son,
Yes.
and he had a marvelous show in the marriage, and it was so well organized. We all went there, all the old friends, they came over, and but that time only I saw a little bit, he's looking a little bit tired, but we didn't take into account. However, I'm sure that Sid is going to take the family name further forward, and we feel bad because we feel that he didn't have enough time to relax for himself, and he could not enjoy the fruit of the labor that he has so diligently fought and earned. But whatever association I had with him, it was all pleasant memories, good memories. So I will tell Deepa that you have the strength, because there is a huge veteran that he left behind. They are there. They all speak good about him, and we are there as a family. Whatever little we can compensate his absence. It is very difficult to do, but we can all try to be a part of that, so that his
Thank
lot.
you. Thank you, Sabha. That means a lot. That means a lot. You are an extended family from the time we have come. We all have been together. It's a very difficult void. Very, very impossible. And you're right, he went off too early. I mean, this was the time for him. He had plans. We were planning to travel, visit. Didn't know how it happened.
Really, it's really very sudden. That's all I can say. But anyway, the memories are fresh. It will never go away.
Yeah. Thank you, Sabdas. Thank you.
May I request Mr. Padmanabhan to say a few words about his batchmate?
Yeah, at the very outset, Deepa, Mala
Hello.
joins me. Hello, my wife Mala joins me in conveying our deepest condolences at the very untimely demise of Satish, unexpected.
Thank you.
A bit too soon, as you rightly said. And Satish and I were batchmates. However, we were not that close when we were in IIT, because we were in two different hostels, far apart, and we didn't have too many common extracurricular activities. However, we became close when we joined MDL. We joined MDL at the same time, both of us, and in the same department. And he was a great support from that time on. We worked together. He was a great support to me when we had all our little rebellions against the MDL bureaucracy. He was a great support. Whether we learned
structural design or not, we definitely learned to play billiards and snooker in MDL.
Yes,
We
he used to love to do that. I remember.
We used to
Yes.
play in the MDL officers' canteen during lunchtime and afterwards, and he was pretty good at both the games.
Yes.
And he tried his best to hone my skills in billiards, but unfortunately, he didn't really succeed. I left MDL in a year, about a year later, but then he continued for another 3 or 4 more years after that. And even after my leaving MDL, we were in close touch. We used to meet almost twice a week for movies, drinks, dinner. Both of us were in Mumbai. It was a nice time. The relationship really flourished, and we were quite close to each other. We even went on a motorbike trip, if I remember. Dilip was with us, I think, and that we went to Pune on a motorbike trip on a rainy night, and then totally drenched. It was an interesting experience. Yeah, but he was a very sportive guy that way, very supportive and sportive chap. And then when he left India, since after that I did not have much contact with him because we were in 2 different kind of areas. But then I watched from the sidelines his meteoric rise in the international corporate world with great admiration and also a bit of vicarious satisfaction. I was very proud to be the batchmate of a person who succeeded in the international corporate world, which is not it's a no mean feat. That is, I was proud because of that. And then, but I will attribute his success to, I think, to his clarity of thought. I think he was never muddled in his thinking. He was always very clear, and I think that added to that his clarity of purpose. I think resulted in the great success that he really achieved.
Very true.
Yeah, and his and these two, complemented by his straightforwardness, made it very easy for us to deal with him, work with him. And even though I did work with him a very short while, we have lost his physical form, but I'm sure he will remain in my memories till the end of my own physical form. There's no doubt about that. And thank you, INA, for giving me this opportunity to reminisce about my dear friend Sateesh.
Thank you. Thanks a lot. I feel so proud to be known as Sateesh's wife because he lived and worked for others. Honestly speaking, for him, he's mentored so many people here. And I'm trying to get to know more about him now after his passing on. People have just walked up and just come and told me things about him. And he was so quiet and humble. He refused to talk about his achievements. I think I, being a wife, is coming to know much more now.
Thank you. Thank you very much. May I request Mr. Sawant, Dilip Sawant, to say a few words?
Yeah, thank you, JD. At the outset, Deepa, my condolences from Sneha and myself.
Thank you, Dilip. Thank you, Sneha.
Yeah, I still remember meeting you in Singapore in 2017 at Jaita's
wedding.
Yeah. Sateesh happened to be my hallmate from Azad Hall. As Sabyadik mentioned, that we were the 5 Pandavas. I met him. He came a day or 2 later in Azad Hall after we joined. Now, very energetic go-getter. I remember once in our 3rd year, the secretary decided to have a badminton court. And it was Sateesh who took a lot of initiative in that, and he would practice late in the nights playing badminton, and eventually he was declared a champion in 3rd year badminton. So he was one person who was always a go-getter to get as many. I mean, he was so very popular in the hall also. And as Sabya mentioned earlier, Padmanabhan mentioned that when Sateesh got a new bike when he was in Mazgondok, we go all the way to Pune, myself, him, and I think it was Desai who was with us, Nishi. He stayed overnight in Pune and then came back on that rainy day. So that was the time when he got his new SD bike.
I remember that bike. When I got married, he had that bike. I remember that.
Yes. So, but now I feel, yes, he has left us quite early.
Very early.
I'll surely miss him. Of course, my classmates will miss him a lot. So thank you, JD, for giving me a chance, and my condolences once again to Deepa.
Yeah, thanks,
Thank you so
Dilip.
much.
Thanks, Dilip. My God, there's such memories. Very difficult. The void is too huge, too huge. And
Thank you very much. Fortunately, I was also fortunate to meet Sateesh and Deepa as well. I first met Sateesh at IIT when he came campaigning for a student Gymkhana post. He used to sport a beard in those days. His bright big eyes and very amiable smile was impressionable, very impressionable indeed.
Yeah.
When I worked with him at MDL from 78 to 82, he was kind of our mentor. I remember spending lovely evenings with him and Deepa, along with my batchmate Venkatesh, who also we lost earlier this year.
Oh, Venkatesh is, he's no more. Oh my God, I didn't know about that. Okay. So sorry.
When I visited NTU to meet my son, who was studying there in 2006, Sateesh came down to the hostel to meet me and dropped me back to my hotel.
Yeah.
During my tenure with L&T Valdil, we engineered the top sides of a few Modec FPSOs, and we met again at his office and we interacted professionally. It was wonderful to have him, giving us the work, and it was really wonderful to meet him again and again. It was shocking for me to hear about his untimely departure. He was one of our tribe who made his indelible mark in the profession internationally, as rightly said by Padmanabhan. May his soul reach Sadgati. Thank you so much to everyone, and thank you, Deepa, for attending this session.
Thank you all for making me
connect
to Sateesh once again with these beautiful memories. Thank you for remembering him. It means a lot. It means a lot.
Thank you so much.
Thank you. And take care. All of you, please take care and stay safe.
And you too, take care. All the best.
Yeah. Bye.
Thank
See
you
all. Thank you. Thank you, everybody.
Thank you very
Bye.
much.
Bye.
May I now request Dr. Iyengar to take over and start our technical session?
Thank you, sir. We started on a somber note. Now it's the time for our technical session, which will be on numerical modeling of wave structure interaction, both fixed and floating. This would be a presentation by Dr. Sriram from IIT Madras. I also welcome Dr. Jalihal, NIOT, who was consented to be the chief guest. The session chair will be Dr. Vishwanath Nagarajan of IIT Kharagpur. Dr. Vishwanath Nagarajan is an associate professor in the Department of Ocean Engineering and Naval Architecture in IIT Kharagpur. His broad area of research is in ship, underwater vehicle dynamics, and fluid dynamics. He is involved in the teaching of several subjects for undergraduate and postgraduate students. He graduated from IIT Kharagpur, BTech in Naval Architecture in 1995. After graduation, he joined as a naval architect in the Shipping Corporation of India, Mumbai. Here he was involved with the shipbuilding, ship construction, and ship maintenance work. During this time, he got Japanese government scholarship to do Masters and PhD at Osaka University, Japan. After completing PhD, he worked for a short time as a postdoctoral research at Busan National University, South Korea. Then he joined IIT Kharagpur in 2009 as a faculty. He has supervised numerous undergraduate and postgraduate research projects, besides guiding PhD students. He has published several papers in peer-reviewed international journals and international conferences. He is involved in several sponsored research and technical consultancy work. Dr. Vishwanath is a reviewer for internationally reputed journals like Journal of Marine Science and Technology, Ocean Engineering, JEME, and Defense Science Journal. He has been invited for reviewing PhD, MS thesis, and conducting PhD by Viva's examination. He has been in the organizing committee of several international conferences. He is a member of the Japan Society of Naval Architects and Ocean Engineers. With this, sir, I'd invite you to chair the sessions, Dr. Nagarajan.
Thank you, Dr. Iyengar, for your presentation. And also I welcome all of you to this INA technical session, numerical modeling of waves, fixed and floating structure interaction. So first of all, I will welcome Dr. Purnima Jalihal from NIOT. So thank you, madam, for joining us in this session. So Dr. Purnima Jalihal is a senior scientist who heads the Energy and Freshwater Group in National Institute of Ocean Technology, India. She has coordinated many first ever projects in ocean energy and desalination. She has a tremendous contribution in setting up of first ever ocean thermal gradient based desalination plant at Kavarati Island in the Lakshadweep in Arabian Sea, which helped in transforming the lives of a small island community which had a serious lack of drinking water. For this work, she was awarded the Vishwakarma Medal in the year 2006 by Indian National Science Academy. This success led to more establishment of more plants in the island and also a scaled up demonstration plant offshore. She also led device development for harnessing ocean energy from waves, marine currents, and ocean thermal gradient. The wave energy powered navigational buoy for use in ports has been demonstrated successfully and has now been transferred to the industry. So the marine hydrokinetic turbine was successfully demonstrated in the Andaman Island area, and the first ever wave energy powered desalination system was also demonstrated at Vizhinjam, Kerala. Currently, she is focusing on scaling up and is also leading the first ever OTEC powered desalination plant in Lakshadweep. She has a PhD in civil engineering from Duke University, USA, and she is on many committees of Indian government organizations related to water and renewable energy. She also has been the chairperson of the Indian Desalination Association Southern Zone. She was awarded the Uehara Prize for the year 2019 by the International OTEC community for contribution to the development of ocean thermal energy conversion. She is the European Union-led Clean Energy Mission Innovation Champion for India 2020, and currently she is serving as the chairperson of the Executive Committee of Ocean Energy Systems Technology Collaboration Program, TCP, under the International Energy Agency. So I once again welcome Dr. Purnima Jalihal. Thank you.
Very much.
So now, shall I introduce Professor Sriram?
So we can go on with the lecture with the permission of the Chief Guest. Yes.
Yes. Kindly introduce Dr. Sriram, Professor Sriram, before the lecture starts.
Yes. Okay. And also, I welcome Dr. V. Sriram from IIT Madras Ocean Engineering Department. And thank you, Dr. Sriram, for consenting to give the seminar in this INA technical session. So Dr. Sriram, V. Sriram is an associate professor in the Department of Ocean Engineering, IIT Madras. His research work focuses on computational and experimental hydrodynamics. He has developed state-of-the-art numerical models applied to ocean engineering, particularly coastal and offshore engineering. And he received many awards, such as the Newton International Fellowship from the Royal Society UK in 2009, then Alexander von Humboldt Fellowship from AVH Foundation Germany in 2011, then DST Inspire Faculty Award from Department of Science and Technology, New Delhi, then thereafter R.J. Garde Research Award from Indian Society of Hydraulics, and thereafter Young Faculty Recognition Award from IIT Madras in the year 2018. Then he got this ISOP, that is Indian International Society for Offshore and Polar Engineers Session Organizer Award 2020. And recently he received the DFG Marketer Professorship from the DFG and LUH organization, Germany. He has published more than 80 papers in international journals and conferences. And presently he is leading the Center for Large Scale Ocean Research, that is from India IOE funds of IIT Madras at IIT Madras in collaboration with 16 international faculty from 10 different countries. So it's a very good achievement by Dr. Sriram. So I am sure you all will enjoy his session, and it will be a great contribution to our community. I once again welcome Dr. Sriram, and please, I request him to continue with his presentation.
Yeah, thank you, Dr. Vishwanath, and thanks for giving me the opportunities at INA to showcase some of our research work which we are carrying out at IIT Madras. So I will just share my screen. Whether you can able to see my screen?
Yes, please.
Yes, we can see it.
Yeah. Okay. So I'm just switch off my video because of transmission rate. Okay. Fine. Okay. Thanks for once again. Thanks for giving me an opportunity to present in INA forum. So my topic would be on numerical modeling of wave structure interaction. So in this particular talk, of course, when you say numerical modeling, there will be equations. So I'm not going to show you any of the equations, but rather I will try to show you the applications of our numerical model which have been developed, particularly at IIT Madras, as well as what are the different challenges as a numerical modeling it encompasses, and then how we can able to model efficiently to cater to the challenging environment of the ocean waves. So my overview of my talk would be mostly on the modeling approaches, as well as the different class of numerical models, as well as the application of these numerical models to the field problem, as well as to the some of the laboratory experiments which we compare, as well as one of the major contribution which we are trying to do is basically the hybrid modeling for the wave structure interaction, because many people may be already using a Navier-Stokes solvers wherein it takes computationally very high time. So in order to reduce the computational effort, we venture into this hybrid modeling, which is we are developing for the last 10 years, this hybrid modeling coupling approaches, different approaches. I will talk about the different types of coupling modeling, as well as what are the different the open source part which we have released it for the public use. All these things I will try to cover up in this talk, as well as finally I will end up with one of our center, which is a Center for Large Scale Ocean Research, wherein we are going to consider one of the largest flume, academic flume, as well as facilities to cater to the large scale research. So what are the challenges, particularly if you look at the challenges in the extreme sea modeling? So we have a large sea area, as many people are, as most of you are ocean engineering, so I don't need to tell anything in detail. And these are highly nonlinear wave conditions that exist with current. And of course, one need to consider depends upon the problem, whether the turbulence is going to be important or not. And you are going to have a lot of aeration impact, hydroelasticity, and all these uncertainties which is present in it. And if you look at the existing software or the models, of course, we have a CFD packages, which is a time-consuming one. And the other end, for the last 20 years or so, people have developed the fully nonlinear potential flow theory, which is, of course, invisible and irrotational. So you can't model the breaking waves or the aeration part in it. But of course, it gives most of the things for the design of a structure, any structure. But the other approach is a promising approach is the hybrid modeling, wherein in the far field, we try to use a potential flow solver, wherein near to the structure, we try to model use a Navier-Stokes solver, that is a viscous modeling. So this is one of the promising approach, wherein we can also combine with mooring line if you want to model the mooring line along with the elastic structure, and so on and so forth. So in this entire talk, we will be trying to cover about the last three parts, that is the FNPT model as well as hybrid model, as well as the coupling with mooring line tension as well as elastic structure interaction. So in general, when you try to talk about the fully nonlinear waves, violent wave and structure interaction, we have different class of numerical models. Depends upon the method. We call this a mesh-based method or the mesh-free methods. Mesh-free methods are recently quite popular for modeling the wave structure interaction process. And then in the potential flow solver, of course, traditionally people have used boundary element method, and then we can also use finite element method. So the blue one, whichever I have highlighted over here, is the one which we are trying to which we have developed at IIT Madras. And I will be trying to show these different models for the application of ocean engineering community. And one of the important thing in the numerical tool, whenever you try to develop a numerical tool, it has to handle both the small waves as well as the steep waves, because most of the commercial code may not be able to handle the small waves to the wave structure interaction process, because there will be a lot of damping and numerical dissipation and so on and so forth. And it has to also capture the splash up or plunging of the waves along with the structure interaction, whether the structure can be a rigid or a floating, a rigid floating structure or elastic structure interaction. And more importantly, for industry perspective, because when I started after my PhD, I worked in industry. When we tried to do it in industry, they need computationally efficient as well as a faster one. The simulation has to be computational time. Simulation time to be very less. So that is one of the way which we have to look into whenever we want to see for a numerical tool. So at IIT Madras, we try to develop different time domain models. The one is the traditional one, the Navier-Stokes models, wherein depends upon the computational domain as well as the size. It may take months or weeks, wherein the physics and accuracy will be much higher, where the computational cost is also going to be higher. And the second class of problem is the fully nonlinear potential flow theory, wherein depends upon the computational time, it may take hours. I mean, the computational domain as well as your problem of interest, it may hardly take an hour, or it may take, sometimes it may take a maximum 24 hours, that's all. But the physics, of course, we are using a potential flow theory, so we are just trying to do some kind of assumption in it. So the physics is a little bit accurate, not compared to the Navier-Stokes model. And the third one is the Booth-Nix model, which is depth integrator or depth average models, wherein you can able to model for a large domain. Maybe if you want to have a kilometer of domain size, you can able to model by using the Booth-Nix model. And the last one is the hybrid modeling, which we will be talking about in this talk about fluid structure coupling, wherein we are trying to couple different aspects, but different physics, and try to merge into one particular tool, so that you can able to have very less computational time, as well as you can able to have approximate the physics much better. So in this slide, I'm not going to go into the equations part of it. As I told you in the beginning, I will just try to show the application of the developed model for the different approaches which we have developed. So the first one is, I will show about the mesh-free method. So what is mesh-free method? So when people might have known about the finite element or finite difference, which is a mesh-based method, wherein mesh-free means it's basically we are trying to deal only with the nodes or particles. There is no need of any mesh. So is it a new thing? No, it's not a new. It basically exists ever since the Taylor series exists. So the advantage of this mesh-free method is it has because the finite element or finite volume method, you need a high cost in creating the mesh, as well as you need automatic meshing when you want to do a dynamic mesh simulation, as well as it has a low accuracy of the stresses, because the derivative term will be low accurate in the case of a finite element, and there will be discontinuities at the element. So these are all the issues in the mesh-based methods. And of course, adapting to the dynamic mesh as well as the time stepping is challenging in the case of mesh-based methods. And if you want to deal with a very large deformation problem, again, the mesh has to be properly refined. And one of the major issues in the is in particular in ocean engineering is the free surface, which is an unknown. Okay, so we have to find the free surface during the simulation itself. So what is this mesh-free method? What is this particle-based method? So the particle-based method, this is the only slide which I have the equations, but what is this particle-based method? The particle-based method is exists ever since the Taylor series expansion exists. But I mean, the issue is if you might have used the one-dimensional Taylor series, it's basically, you might have studied in a higher secondary school itself. It's basically you get the forward difference or backward difference and so on and so forth by using the Taylor series. But one of the constraint in a one-dimensional Taylor series is the path. That means it has to go in only one direction. But how about two-dimensional or three-dimensional Taylor series? Of course, yes, you can use a two-dimensional, three-dimensional Taylor series. But the advantage with the two-dimensional, three-dimensional is if you want to define a point, it's enough if you know the X, Y, and Z coordinate system. So that means you don't need any mesh at all. You can just need to know only X, Y, and Z coordinate system, and then you can able to solve this. Suppose if you want to use for a 5 derivatives, you have to pick 5 points, and then you have a 5 equations, and then you can able to solve for the 5 unknowns. But the advantage is it has no path constraint. But the disadvantage is it needs more nodes for the cross derivative terms. Particularly, it leads to ill-conditioned matrix. So that is the reason people before 40 years, because the computation is not that much, so they have not tried and improved these two-dimensional, three-dimensional Taylor series expansion. So nowadays, in the last 2 decades, the people, because of the computational power, people try to improve upon this method. So that leads to the particle-based method. So most of the particle-based method which exist as of now can be derived or can be re-derived just by using a Taylor series expansion. So that is all. It's about the particle-based. Why there is the mesh-free method? Because the two-dimensional Taylor series itself is a mesh-free scheme. So the one scheme which we are trying to work on for the last 15 years is meshless local Petrov-Galerkin method. If you are familiar with finite element, you might have heard about the word Galerkin scheme. The Petrov-Galerkin, in the sense both the test and trial function will be in different functional space. And the local means we are trying to deal with the local subdomain instead of trying to do the entire subdomain, entire the global domain. And meshless in the sense there is no need of any mesh in this particular method. And there is an improvement which we have made in this particular meshless local Petrov-Galerkin scheme for the velocity as well as for the updating the coordinate system. So this has been developed for the past 15 years, and we have applied to a wide variety of problems. And recently we come up with the review paper on this particular MLPG, particularly the developments in its application in ocean engineering contest. Wherein we detail the algorithms, each and every algorithms, and discuss the pros and cons of these algorithms and compare it with the traditional smooth particle hydrodynamics, which is another class of particle-based method. I'm not going to deal about any of the equations because of the audience. I will just trying to focus on the application of it. So we try to develop this particle-based method. Say, for example, some of the applications which we have applied this model is for the sloshing problem. It's a two-dimensional tank, as well as for the wave overtopping on a structure or the wave breaking on a simple slope. So this is for a typical two-dimensional test cases normally people will do whenever they try to develop any numerical scheme. And we also extended this two-dimensional model for a wave breaking interaction with the wave breaking interaction with the elastic plate. So whenever there is a plate, a vertical wall or such, it is going to have an impact, and then the plate is going to vibrate. So this entire process has been captured by using a two-dimensional model, wherein we have particles which are coming and hitting an elastic membrane, and the elastic membrane is going to bend. So you have to solve the elastic structure interaction, the traditional Euler-Bernoulli equation based on finite element, as well as we solve the fluid based on the meshless local Petrov-Galerkin scheme. And we try to understand how it basically compares with the experimental measurement. So we had a comparison with the experiments as well as the numerical model. The one which is on the left-hand side is an experiment, and the one which is on the right-hand side is a numerical comparison between the two things. And this is for two-dimensional. So first I will just show the two-dimensional applications, then I will go to the three-dimensional application. So the another application which we considered is about the porous structure interaction. Normally for modeling any rubble mound breakwaters or stones, we consider as a wave porous structure interaction. There are two ways of modeling. One is by using a macroscopic approach. That means you model each of the rigid bodies. Okay, so that is currently we are working on that particular problem, wherein the computation time will be very much expensive. And the other one is a macroscopic approach, wherein we try to model this porous membrane also as a fluid, but by including the Darcy velocities and all those additional terms which comes from the empirical formulas. So this is one of the applications wherein we extended it to the wave porous structure interaction, as well as we extended it to the wave vegetation interaction, wherein we this is one of the recent due to the climate change adaptation of how to protect the coast based on the vegetation part. So we extended it for a two-dimensional. Of course, we do have a three-dimensional model for the same thing. How the vegetation is going to influence the damping characteristics of it. So this is another application of this particle-based method. And then, of course, we applied it to the floating bodies, typical monohull as well as a twin hull. This is for the forced motion, and we tried to use the particle-based method. One of the issues basically in the particle-based method is that it cannot handle a variable resolution like in a mesh-based scheme. Because of the algorithms which we use. So in the recent years, we try to improve upon this particular algorithm wherein you can able to adapt it for a gradient mesh or like in the mesh-based schemes. So that is one of the advantage which we have recently focused on modeling the floating bodies. And then the advantage with this one is we can able to reduce the computational time drastically. Of course, everybody knows that near to the body, we will try to have a finer mesh resolution, and far away from the body, we will try to have a coarser mesh resolution. And then you can able to reduce the computational time as well as the number of nodes that is required to capture the particular physics which is involved in it. And then, of course, we applied it for a simple free decay test as well as for a roll motion of a box, wherein some traditional experiments are available to compare with the test cases. And then we also applied it for a floating body, a response this is for a two-dimensional, and then I will show you the three-dimensional in the coming slides. And one of the advantages, we can have a very adaptive particles, as well as we can also have a green water loading if you are interested in all. That is easy to handle in the case of a particle-based method when compared to the mesh-based scheme because of the advection term, which is not present in this Lagrangian-based formulation. And recently, we also did for two boards typical application for FPSO nearby the tankers, and how do they respond? What is the gap resonance between the two things? And we did small experiments in the lab, and then we compared it with our numerical model for a very steep cases. So these are some of the things which are already been published in the journals. And these are the previous ones are basically a two-dimensional. Of course, the two-dimensionals are not of a practical importance. Of course, it is of most of academic interest as well as for the testing the numerical schemes which are adopted. And the most important one for the practical application is the three-dimensional modeling. So, of course, we extended our particle-based method for a three-dimensional modeling. But one of the issue is the computational time in these modeling. So I will come back to the how we address this computational time in the later part of the slides. So this is a typical application for a fixed structure as well as for a floating structure or for a heaving cylinder. So you can apply it, and then this is a comparison with experiments for a simple 3D boards. And this is for the two-dimensional one, which is based, mesh-free methods based on the Navier-Stokes model. And I will just show you the mesh-based method which have been developed. This is recently we developed this particular model, which is of course open source. We released it to the public. Of course, anyone can use it. This RANS 3D has a lot of capability. It is based on the two-phase flow model, and the previous one which I showed is basically a single-phase modeling. And we try to optimize it when compared to the traditional commercial package by using the hybridization by using the potential flow solver. I will talk about that in the coming slide. As well as you can able to use this model for a long duration as well as for a long time. And then we developed a lot of different schemes for the VO part of it. And this is a traditional test cases wherein you try to do a dam break impact on a simple structure, and then you try to validate with the experimental measurement and show whether your free surface tracking scheme or your buoyant volume schemes are working better. So this is a typical application of it. And then we also try to do some of the three-dimensional solitary wave braking on the slope, wherein we also develop the conservative form of the solver as well as a non-conservative form of the solver to handle the braking jet properly. So because in most of the non-conservative solvers, we can't able to handle the braking jet properly. So we want to understand the braking jet characteristics with the turbulence very properly. So we move to a conservative solver. And this version of conservative solver will be released it will be released in a month's time. Sorry. Yeah, and then of course this is another test case which I showed you for the twin bar, that is a twin hull for a fixed hull. Of course, this is a fixed hull. This is a simple validation test case. We want to understand the watericity behind it by using the PAV measurement, which we made in our laboratory, as well as we compared it with our experiments with the numerical model which we have developed in this particular one. And of course, the last one is we also try to simulate for a long duration. One of the aspect is most of the Navier-Stokes models may not handle for a 300-meter domain size or with a 5-meter width. So we want to handle this large-scale log duration problem. This has been efficiently done by using the proposed model which we have developed, and it is being released, and we can see the comparison between the experiments as well as the numerical, both for the run-up phase as well as the drawdown phase of it. And of course, this is one of the projects which will be funded by NRB. Recently, they have just sanctioned this particular application. So far, we have applied it to the offshore and coastal engineering. So we want to apply it to the naval architecture problem. So recently, we want to apply this RANS 3D solver for the naval architecture applications, particularly for the ship resistance as well as for the forward motion of the ship. So we have the present model, the RANS 3D is what's based on the embedded mesh. So you really don't need to have a very difficult time in creating a complex mesh. It comes up with it because we are trying to fine tune it for different, particularly based on the offset tables, particularly addressed to the naval architecture applications. And the second class of the problem is fully nonlinear potential flow theory. So this potential flow theory, we have been working on this. I mean, this is my PhD topic. So this version of the 2D code has been in public use, and a lot of my colleagues in abroad, they are actually using it for most of their applications whenever they want to test it in the facilities. And we will be coupling this potential flow solver as well as the Boosnik model, which I'm going to talk with the Navier-Stokes model, that is our hybrid modeling. And the Boosnik model is basically a finite element depth averaged model. Of course, we can able to model large domain like the Chennai port, modeling the Chennai port, and so on. But one of the interesting effect is the ship wakes on the banks. Whenever you have a narrow channel, there is going to be when the ship is going to move around in the narrow channel, there is going to be a bank erosion. So this is one of the problem in the Hooghly River. We did some measurements, and then we want to develop a numerical model to address this particular problem. But of course, using a CFD for this is not feasible. So we resorted to that's why we developed this finite element based Boosnik model, wherein we can able to move, but it is approximately we can able to generate the ship generated wakes by using a moving pressure field. But of course, it can handle both the slender as well as the bluff shape of the ship bodies, and it can also move the orbitary motion. But of course, you can't have an exact resistance, wave making resistance like in a CFD code, but it is just approximate. Mostly it is based on hydrostatic part of it. And this is a typical ship moving pressure that is moved in the constant water depth. And we want to validate this. Of course, the validation is a tedious part. So we actually, one of my colleagues did some field experiments in Baltic Sea in the Italian Bay when there is a ship which is moving from one end to the other end. They measure the ship path as well as they have the entire bathymetry as well as they have the wave gauge reading near to the island. And this is mostly the calm sea area, so there is no waves. Most of the waves are generated by the ship wakes, by the fast ferry. So we did these simulations by using our developed model for the ship wakes, and then we tried to compare our model with the field measurement. This is, this is a field measurement, the time history, as well as our model, along with some of the existing other model which is available in the open source. And we could able to capture very well, particularly when you say that it's a field measurement, we can able to even capture the high frequencies as well, all the types of frequencies that exist that has been captured by our numerical model. So then we try to, then we want to see when compared to the existing model, one of our advantage of our model is we can able to do a curved path, which is challenging in the case of other finite element, other Bosniak types model, which are based on finite difference as of now in the open source. We developed some of the different schemes to handle these curved paths when the ship is going to move in the curved domain, and how the wakes are going to affect the banks, as well as by using a traditional sediment transport formula, we can able to calculate what is the rate of transport of the sediment and how the bank is going to erode. And we are in the process of comparing it with the field measurement as of now. And the last part is the hybrid modeling. So one of the typical applications of hybrid modeling, I want to model a very big domain, and then I want to also interested in the viscous characteristics near to the small modeling. So one of the advantages, you have the potential flow model in the far field, and then you want to study the near shore, just the viscous effects just near to the structure, or when there is a ship which is moving around it. So in those cases, we use the Navier-Stokes solver, which have been developed, as well as we use a potential flow solver. So that means you need to have a hands-on experience in both the solvers in order to couple it. So that is how we can able to reduce the computational time. One is, of course, you put it in the GPU with the clusters of mega servers and do it. That's what normally people will do it. The second one is based on the physical-based approximation. We have potential flow models, different types of potential flow models. We have different types of Navier-Stokes models, and we want to couple these two models together. So the red ones are basically the models which have been developed at IIT Madras. To be frank, I am not using any of the open source the open source or commercial solvers. All the solvers have been developed in-house at IIT Madras. And we want to couple these two solvers in order to have the advantage and disadvantage of these both the methods to make it a unique one. So there are different types of coupling which are available in the open literatures. I mean, we have discussed a lot of different approaches. One is based on the domain decomposition. That means you divide the domains into different parts and then handle it, either by passing the information from one solver to the other solver, or you try to do a functional decomposition. That means you try to separate the irrotational as well as the rotational flow characteristics together. And then whether we can handle it with structure as well as without structures. At IIT Madras, we are developing in both the trees. That means we do have a domain decomposition based approach as well as we do have a functional decomposition approach. The advantage of the functional decomposition approach is that it is computationally very, very cheaper in solving your Navier-Stokes solver. Where in the case of domain decomposition, you have to solve the Navier-Stokes solver as such. Initially, we try to develop this two-way, because that is a two-way is a challenging one. That means you have to transfer the information from a potential flow theory to a Navier-Stokes solver, both in the space as well as in the time. So we developed different schemes to address this particular approach. And then we tested with the standard, some of the benchmark problem, wherein this red one is basically the potential flow region. And then this colored one is basically the Navier-Stokes solver based on particle-based method. And then we try to transfer the information from one domain to the other domain smoothly without any issue. So the advantage is you save a computational time of about 8 hours for a two-dimensional problem. Then you can imagine the savings in computational time for a three-dimensional problem. So then later on, again, the 2D approach, we try to couple it with the elastic solver, wherein we have a potential flow domain in the far field. We have a Navier-Stokes domain near to the field. And then there will be a streamless coupling between the two solvers. And then it basically interact with the elastic structure. Okay, so all these are 2D. I will show you the 3D in a short while. So these are different approaches wherein we first test it for a 2-dimensional problem, which is of academic interest, as well as for testing our numerical schemes as well as the approaches. And then we basically go for a 3-dimensional approach. So now coming back to the 3D hybrid model. So the 3D hybrid model is a challenging. One of this problem is the cylinder. It's a simple test case which we released in the ISOP, which is one of the international conference, wherein I headed the comparative study session, wherein we released the data to the open public. And then we asked for people from different parts of the world to participate in the comparative study. We did 2 different cases. One is with the fixed cylinder. Another one is the moving cylinder case. That is, moving cylinder is basically a forward speed problem with the incoming waves. This is just an idealizing condition, but of course we are not doing a ship because that is going to be complex. So we want to start with a simple problem. So we released mostly the data for the non-braking, because the braking case is a challenging one. So we don't want to complicate the problem. So we released it for the non-braking condition, and we received about 20 different participants who used various types of solvers, from commercial package to their in-house solver to the open source solver, and then we tried to get those data, and then we did a quantitative analysis between the different solvers, and then we try to see we don't want to say which solver is the best one. Rather, we want to understand how the solvers are comparing within each other as well as with the experiments. And this is one of the way wherein we can able to see our own solvers, how it basically compares with the rest of the solvers, which are available both from the commercial packages as well as from their in-house solvers. Okay, so we did, there was a 2-part paper wherein we published the guidelines as well as some of the recommendations how to do it. And most of the people, actually, they use a hybrid model. Basically, whenever they use in-house code, they basically use a hybrid model. Whenever you use a commercial package like Star CCM Plus, they use a dynamic meshing, that is a offset grid, and so on and so forth. And can I know what is the time left?
I think you please go ahead.
Okay, fine. Sure.
Yeah.
Fine. Thank you. Thanks. So, now one of the issue with this particular problem, this hybrid problem, hybrid numerical model, is this particular cylinder is being towed in a towing carriage for 50-meter distance. And then it is going to interact with the focused wave, which is focusing at that particular location. So initially it will be only current, a simple current generation, and then it is going to have a current plus waves interaction. So, so we want to test how these are going to. So that was one of the challenge which we posed to the researchers. And the other modeling which we have proposed in this particular one is based on potential flow with MLPG, as well as I will show you with the different other solvers also. So there are different types of coupling, whether you do it in coupling in only one side, or you do the coupling in 2 sides, or you do the coupling in 4 sides. That means you are trying to reduce the domain, the computational domain for the Navier-Stokes solver, or you try to do a cylindrical domain. So that means you just have only the Bosnick mesh, that is a finite element mesh, that is a potential flow solver on the far field, and then you will have only the Navier-Stokes solver near to the structure. And this is a typical one wherein you have a cylinder in the center, and then you have a computational Navier-Stokes domain, a cylindrical Navier-Stokes domain, and then you have a rectangular finite element domain, which is based on potential flow solver or based on Bosnick's model. So for this particular application, it is based on Bosnick model. So we try to derive the results from the Bosnick's to the MLPG. It's basically one-way coupling, and then we compared it with the experiments and so on and so forth. This is how I skipped the animations. I just put this because animations was time consuming. So I just show only the JPEG image of it. So it's basically a cylinder, a vertical cylinder. So you can able to imagine if even you can be able to put a ship, and then you can able to steady only near to the circular domain there is no need of any reflection which is going to come up from the boundary because it is always getting information from the potential flow solver. And the other approach which I told you is the SWENS, that is a functional decomposition, which is one of the method which is being developed by ECN, Equally Central in NAT. And this particular foam star as well as the SWENS solvers or open foam packages, which is developed in-house by BV, Bureau Veritas, as well as ECN. And actually they are, through a collaboration with one of my students, Siddiq, we are trying to apply for some of our application. Then we try to incorporate some of the our own concepts which have been developed in the open foam package. Of course, this is not an open source as of now. It's only mostly used by BV. And one of the thing is we want to state the verification as well as the validation of this particular solver which have been developed. So that was basically done by my student Siddiq. It's based on a one-way domain decomposition, the one which I told you, as well as there is another option wherein we can use a functional decomposition. What is mean functional decomposition is nothing but we subtract the Euler equation from the Navier-Stokes equation, so you will get a complementary solution. You basically solve for the complementary flow field, and you will take the incident flow field from the potential flow solver. So that means you can able to reduce the computational time drastically. So that is one of the advantage of this functional decomposition. So we applied this for the same problem of a fixed cylinder. And then we did the comparative study between different meshes, and then we try to say that the SWENS approach, even with the coarsest mesh, that is by solving your full Navier-Stokes solver. The coarsest mesh is the loss in accuracy is only 10% in the forces, which is of a similar accuracy that of your full Navier-Stokes solving a full Navier-Stokes solver with the finer mesh. So you really don't need to invest more on refining your mesh, a finite volume mesh. Rather, you can have a very coarse mesh, and then you can be able to get the same physics with a very less computational time. And then the second approach, which we released for the comparative study, is the moving cylinder. That is a moving structure interaction. So how do we model this? Of course, we can do physically, we move it in a towing carriage, but how well we can able to move computationally. So there are different approaches. One is we call as a two-way coupling. Another one we call as a one-way coupling. Other one you call as a fully solve the Navier-Stokes equation for a complete domain. Suppose if the towing tank is 80 meter, you use a full towing tank of 80 meter length. But of course, it is going to be computational time. You have to put it in a server with 300 crores or so. That's what one other person did using star CCM plus in the comparative study. So in this approach, what we are basically working on is the two approach. That is the one which we are written as a MT2 as well as MT3. That is, we try to move the structure as well as a Navier-Stokes solver with the reference frame. That means the frame of reference will be, again, the solver will also be moved along with the forward speed, like the one which I have shown you in the bottom figure. The other one is like in a physical tank. You move the structure either by using a dynamic meshing that is based on overset grid, or you can use an embedded machine. So the first one is the one-way coupling, which we did based on the foam star that is developed by BV, using both the Navier-Stokes solvers, so the structure will be moved in the same reference frame. In the second approach, wherein this is based on our IIT Madras 3D, we use a fast fictitious domain, wherein we can able to move the cylinder the mesh will not move, but the cylinder will also be considered as one of the solid phase, and then that will be also moved along with the structure. So I think there will be some delay because of the animations. I'm sorry about it. So I think these animations, you can see it in my website. And this is one way of doing the domain decomposition based approach. The other one is we want to do the modeling the realistic sea state with the offshore wind farms many offshore wind farms. That was one of the things. So the idea is you will have a lot of potential flow solver throughout, and then you will have different Navistar solvers, and then you will try to do it. So that was the futuristic view of us. In order to go about it, we need, for a floating body, we need a mooring lines to be modeled. So what we did was we used one of the open source solver, which is Moored-in, which is available. It has both dynamic as well as static mooring lines it will be solving. So we coupled this Moored-in with our potential flow, with our Navistar solvers. So this was done both at each and every time instant. We solve the rigid body dynamics. We give the response to the mooring line, try to solve the mooring line, and then this mooring line will be fed back to the potential to the Navistar solver, and then it again serves. So it's basically dynamically coupled. All the dynamically coupled. It is not like we are doing an individual coupling. It's basically all put together in one particular tool. So for this, we took experiments which have been conducted again in ECN, because it is part of a collaborative activity with ECN. So they did for a spar, floating spar with the mooring, delta mooring. So we did the moored thing, wherein we use a potential. It's a basin of 50 meter by 30 meter wide. So we use a HOS, that is a higher order spectral method, that is a potential flow solver on the far field. And then we use a Navistar solver, that is a foam star as well as Swens, near to the spar. And then the mooring line is also model based on the mooring. So all the three will be integrated together. So and then we compared our moored decay test, which is done in the computational model with the experiments, and then we try to adopt different types of approaches by using dynamic or by using static. The K is basically over is a static mooring part, the red one, and the foam star is basically the with the Moored-in is basically dynamic mooring line with the experiments. It is reasonably good. This is for the heave decay, as well as this is for the surge decay, as well as we can also we do also have the measured tension in the experiments, and we compared it with the numerical computation. So that is also very decent comparison for the tension. And then of course we did with the compared it with the waves, regular waves for different motion, surge, heave, and pitch, as well as this. The first one is for the regular waves, and the second column is basically for an irregular sea state. So this again we evaluated the performance of both the spectral functional decomposition approach as well as the full domain decomposition approach based on the Navistar as well as HOS method, because the one which is there in the colored one is basically Navistar solver. Far away is all our potential flow solvers. And then we compared both the tensions in the lines, all the three lines. I think I have just showed only the two lines. So there is a third line is also there. So the third line is also have a decent comparison, both for a regular waves as well as for the irregular sea state. And so to summarize, we have a different types of modeling approach which we developed over the last 10 years or so, starting from a particle-based method to the mesh-based methods, and coupling different approach by using a potential flow solver based on the Busniks or based on the potential flow, fully nonlinear potential flow theory, based on finite element or based on the higher order spectral method. And to just the last 5 minutes, one of the things which we have noticed, of course, we need for most of the applications for validating the numerical model. Particularly in the case of ocean engineering, we have to deal with the large spatial domain as well as the large time scale, as well as we have to also deal with the small spatial domain as well as the small time scale. That is an impact problem. So the field study is the best way, but it is due to uncontrollable boundary condition. We can't able to reproduce the entire thing. So one way is try to have a large scale facility. Of course, the one of the reason for going for this large scale facility is, as everybody knows, is the scale effects. Whenever there is going to be a wave breaking interaction with the structure, there is going to be a scale effects because of the air, the compressed air part of it. So as part of the Institute of Eminence from IIT Madras, we proposed a Center for Large Scale Ocean Research, wherein we want to develop a testing facility of a large scale of 500 meter length and 8 meters in deep, and the 6 meters of water depth and 5 meters of wide. And then we formed an international research group with about 15 faculties who want to interact, and then we want to generate the collaborative activity along with the testing facilities. So this is a proposed testing facility which we have proposed, and we are looking for, I mean, we are just getting some details for the funding and everything from IITs. And of course, I have not included NSTL because I have, this is only for the academic institute, which are present all over the world for the industry as well as for the academic researchers to use. So these are 5 or 6 all over the world. And we want to pitch ourselves at IIT Madras for the proposed facility with a large tank with as well as a stroke that can able to generate a significant wave height up to 3 meters with the wave period from 5 to 20 seconds. That is basically based on a piston type wave maker with a 8 meter stroke. And so where it is going to be, it is going to be in our Discovery campus at IIT Madras. So the C is basically the existing port center, which is sponsored by Ministry of Shipping, which is the one as part of this tank. We have taken a small tank out of it, so that is basically intermediate facility for the seafloor, which is 100 meter length and 3.25 meter in width, and it has a large stroke of 4 meter, which we are developing in-house. Nothing is imported. And this wave basin we are developed. I mean, it will be in commission in another 3 to 4 months. And we are deploying 152 waymakers. All these waymakers are in-house developed. Nothing is imported. The technology, the design, and everything. Because of our expertise in the numerical model, we can able to develop these experimental facilities for the waymakers and everything. And this is a basin of a shallow basin, mostly for the port and coastal engineering. Of course, you can also do the maneuvering study for the shallow water. And the large scale facility is part of the D, which is there over there in the top figure. The D, which is mentioned, is basically the large flume, which is proposed one. I hope someone will take it forward from us. And in the future, we want to couple the numerical models. So our main aim is to couple, because as part of the center, we are also having a ship simulator, 360-degree ship simulator. The simulator will also be integrated with the wave basin, shallow wave basin. So that was one of our idea. And we want to integrate this with our numerical model. So whether is it feasible? Yes, we have proven this integration of numerical model to the experimental facility way back in 2014 in a 2-dimensional facilities in a large wave flume. This again, it's a large wave flume in GWK in Hanover. So we proved the capability of a potential flow solver, which have been developed by IIT Madras, and how it is been able to trigger the wave maker, and then you can able to reproduce the entire thing in one go. So that can able to do it in the coupling the future models with the experiment. So that was our aim. And finally, I would like to thank my students who are the backbone in developing these models, as well as I would like to acknowledge many funding agencies, both DST as well as the international funding agencies for funding our work on development of these numerical models. Thank you.
Okay. Thank you, Dr. Sriram, for a very nice and presentation. So it has given a wide gamut of application for this experimental and numerical methods for this fluid structure interaction. So now I think there are quite a few very good industrial specialists and like people with a good background in industry. I will request the audience to have some questions. So you can either
Yeah, stop the sharing. Yeah.
Before the audience question comes,
Yeah.
may I request the chief guest, Dr. Jalihal, to say a few words, and then we'll have the question and answer session.
Definitely, yeah, please.
Yeah. Thank you.
First of all, thanks to INA for inviting me for this. In fact, I'm the gainer after listening to Dr. Sriram's wonderful talk. I'm really impressed, and thank you very much for inviting me. But before I say a few more things about Dr. Sriram's work, I just want to say that, it makes me really happy that INA is taking so much effort to put together these kind of talks, because we need to keep updating ourselves in what's happening around us. And these are the real, these kind of talks we don't come to, being in the industry, most of you, including me, we don't get to hear these kind of talks. Earlier I used to do this kind of thing. At this point now, it's become so administrative, and, it's really a refreshing change to hear these talks. So I must first of all congratulate INA, and I appreciate Mr. Das Gupta's dynamism and his interest, and he keeps wanting to hear more and more of different topics. So a hearty congratulations to INA for organizing these lectures in the first place. And of course, thank you for inviting me, for being a part of it. Now, coming to this topic itself, it's a absolutely most important topic for naval architects, for offshore engineers, and we have been struggling with a lot of complicated problems where we don't know how to solve them. I'm so happy that just next door we have a budding young person who has really learned so much and done so much work in the last decade. Well, my crib always had been, in fact, to seniors, even in general committees of not related necessarily to offshore structures. The mathematical rigor is kind of, dwindling of late in this generation. And I used to rue the retiring earlier faculty who had strong mathematical rigor, and who used to guide us into how to do these kind of complicated analysis, numerical as well as experimental. So Dr. Sriram, I am so happy to hear your talk today, and it was really, really very nice, and also eye-opening, because I didn't know that you have been doing so many interesting things. So I heartily congratulate you, and I think I have found the right person now to start interacting for some of the problems that we are facing and which we have not been able to. We depend a lot on ready-made software. So here is somebody who has done the software themselves. So the numerical computations of late, as with the advent of the computer, all of us know that we really got into this numerical regime, and more and more difficult problems we are able to solve today. Can I also ask him a couple of questions, if you don't mind?
Sure. Yeah, sure.
So let me, taking advantage of the label of chief guest, let me start the question session by asking Dr. Sriram a couple of questions myself. Okay. So this is just to understand, and so that I will learn. A lot of things you obviously didn't show all the equations, but you did show all the results or whatever. See, we, as you know, in ocean technology, we don't really deal too much with the actual ship and those kind of moving propulsion and those kind of things. But offshore structures in many ways do we encounter, and we encounter very strange and unusual problems, because we design, some things which are being done for the first time. So one thing is, can your software handle, not only the particle-based one, even the latest one, the hybrid one, which you're talking about, will it be able to handle flow separation? Okay, that is one question. Then secondly, I have three questions actually. I'm sorry, Mr. Dasgupta, but I can't resist. Okay. Then the second one is actually, how will it handle elastic structures? Like really elastic, where the structure actually should change the wave field around it. How much of that can be done? Because also the stresses and deformations involved in that kind of elastic structures, many times we have these connects with FE software like Abacus or something like that. So what do you do? I mean, what does your software do? That was the second question. And the third question is, you were talking about mooring lines and the 3 mooring line results that you showed. Of course, star CCM, we're able to do that as well, but I've never trusted the star CCM results. If a mooring line goes slack, okay, which happens a lot of times when the wave direction changes or the current changes. So if a mooring line goes slack, how would that be taken care of in your software? Okay. All of you, once again, thank you so much for giving me this opportunity. And Dr. Sriram, hearty congratulations. It was a wonderful talk. Okay. So I hope you can answer my questions. Thank you.
Sure. Yeah, thank you. Thank you, first of all, Dr. Purnima, for the nice words, whatever you said. So regarding your questions, first the flow separation. Yes, both the IIT Madras 3D, which is released as of now in the open source, can handle the flow separation part. There is no issue in it because we have already addressed it for a vegetation cylinder. To put a name, because I don't know what application you're thinking, but just to give a context, we did a lot of cylinders to represent the rigid vegetation, and the interaction between the vegetations can be the vortex shedding and everything can be captured. So mostly that is what you are trying to for the mooring line cables and everything. So that can be handled, the flow separation with this one. Regarding the elastic structure interaction, as of now, we are only in 2D phase. The particle-based method, which I told you, the 2-dimensional one with the elastic beam, is the one which is tested case. But for the RANS solver, as of now, we have not coupled it with any of the finite element elastic part of it. But we are in the process of coupling it with one of the other open source one, which is a Project Corona. We are in the process of it, so it may take some time. But hopefully we can able to do that part in near future. That is one part. But as of now, the existing open source which we released in the RANS 3D can handle only the rigid structures. Even the floating body we have not incorporated. The floating body is part of the NRB proposals which we submitted. So the last part is regarding the mooring line. Yes, for the mooring line, as of now we are coupling it with the moored in, which is from the NREL. So we have just used the existing open source tool to merge it into our thing. So whenever they update their open, because that is a fast growing one in the NREL, they are keep on updating their versions. So we don't want to really develop each of those tools, correct? So that will become a complicated process as such, and it is very difficult for me to handle with the students to do it. So that is one of the reason we try to use the existing available open source which are proven enough to couple it with our fluid based solvers. So the moored in, basically we take it from that particular dynamic mooring line. So if there is a slack, it actually handles it, to my knowledge. So obviously it will handle this part. But this particular moored in software is being coupled only with the Foamstar, which is a BV and IRITA ECN. It's not coupled with our IIT Madras 3D. So which we will do it in near future. So after that we can use it hopefully, because that is from BV. So I don't know what is the procedure, but this we will do it in very shortly. Yeah. Thank you. Thanks.
So I will request other members from the audience and especially from the industry to please ask your doubts and clarification. And as Dr. Jalihal told, so nowadays this foreign softwares are very expensive, and Dr. Sriram is making so much contribution in developing the in-house code. So I hope some of the participants will be very much interested in using that. So please, I welcome all of you to please feel free to ask any doubts or questions you may have.
Can I just make 2 observations? This is regarding application only. One observation is, as you have rightly shown in your presentation, the application onto offshore floating wind farms and wind turbine, the columns. So the application, I think, will directly be there with regards to the amount of wave force that will come on the foundation of the floating foundation of the wind farm, which is one of the major areas in which the direction of the industry will go. The second thing is, along with Dr. Jalihal, Dr. Purnima, that is regarding the umbilical and for the Modec services with the power generation or freshwater generation. So the umbilicals have fairly large diameter pipes which go very deep, almost more than a kilometer down. So this application also should be possible to find out how much is the total load and tension and stresses and strains coming, which we were not able to do earlier. So I think this application can be very well done now. So these are two things. And I have one, if I am allowed to share the screen, I can show a very interesting wave, which I luckily received today. And it's really a wonderful picture of what the actual ocean wave, a breaking ocean wave, which comes, and that's especially near the shore area. So I'll just show that for the benefit of everyone. And I hope that you would be able to appreciate the wonder of it. Thank you very much. Okay, that's all. I felt that it is really a wonderful thing that what Dr. Sriram is trying to model, and he has been able to model it with regard from what he showed. So that's my observation. So thank you very much. I don't have any other question.
Is there any other question from the audience? If not, maybe I had a few, so I thought I will. Okay, so one is, as Dr. Jalihal already pointed out, so Dr. Sriram, can you explain little bit more on which type that elastic membrane problem you had explained, So that's a very, very interesting thing. So maybe some of us may not be so much familiar with that. So little bit of actual industry problem and what is the nitty-gritty behind. Can you little bit elaborate on that more?
You are talking about the elastic structure interaction, correct?
Yes,
Wave
yes,
and
yes.
The particle-based method, correct?
Yes.
Yeah. So actually, that was one of my, that was my postdoc work. Basically, we want to model the elastic structure. Actually, what Dr. Jalihal asked me whether when the wave is going to break, the structure is going to bend. Okay, so you have to solve the we solve the finite element Euler-Bernoulli because it's a two-dimensional problem. So you basically solve the Euler-Bernoulli's equation, and then the deformation has been fed into the fluid solver, and the fluid actually take care of the deformation, and the deformation will be felt once again. So it's basically a two-way coupling. So basically you get the information, but it is a partitioned approach. We call it a partition approach because there is another way of doing it. It's basically monolithic coupling, which normally they do it in the aerospace engineering. So here we do a partition-based approaching. The advantage of using the partition-based approach is we can couple it with any of the commercial software later on. So we don't need to really keep on develop because these are two different areas. Structural mechanics is a different area and fluid mechanics is a different area. So we don't. So that is why we want to enter into the partition-based approach. So we basically solve the Navier-Stokes solver, and then that particular information will be the forces will be calculated, and then it will be solved the elastic beam, and the beam deformation, that is the displacement, and everything will be fed back to the Navier-Stokes solver. So this is the one-way coupling of. So the issue over here is the iteration. So whether we have to keep on iterate between the two solvers, or we have to just stop between only one iteration. So that was my entire work, wherein we tried to accelerate the convergence by using a Atkinson relaxation procedure. So that was the one which we did in the iteration part of it. But normally, traditionally, what people will do is they will just feed the information from one part to the answers or whatever may be, and then they will solve it. Or they can also bring it back, but they will do explicit coupling. What we propose over here is implicit till it converges, because that is the issue in the wave breaking. You will not have any issue for a non-breaking cases when there is when the entire structure is under the water. There will not be any issue. But when there is going to be a free surface is discontinuous, at that time the iteration, convergence of the iteration will become very issue. So that is one of the issue which we try to address in that particular work.
Oh, thank you. That's a very, thank you for the explanation. And second
Yeah.
was you had shown a very nice application regarding the sloshing. So, and I think that is a very good industry problem. And many of us in the shipping field, especially in our oil tankers and gas carriers, we have a, because now we have a restriction, many times we are allowed asked to investigate whether the partially loaded tanks are safe or not. So that application also, can you little bit elaborate more? So can we go for this spherical type of tank, or like we have, you have only shown rectangular.
Today, I have just,
sometimes,
exactly. So the one which I have shown is only two-dimensional tank. That is on the particle-based one. But of course, we can do the three-dimensional tank. I have not done the application as of now for the three-dimensional, but of course, I foresee that it's about the person to apply it. Okay, we have developed this tool, right? The RANS 3D that is based on particle-based method. That also can be used, or you can also use, because the particle-based method we have not released it because it is under development. That's all I can, because only our students, when I need to tell what are the parameters to change. But in the case of RANS, which we released it, there is no need of any fine tuning from our side, so anyone can use it. So in that, of course, one can model the 3D tank without any issue. But the thing is, we have to check. There are two ways of modeling a sloshing point. Either you can move the entire tank as such, but that is a mesh problem. Other one is we can try to add the source term and the momentum equation that we have not done over here in this the tool which you have released, in the RANS solver which you have released. But that application can be taken up. Okay, but this is, each and everything is a different aspect to deal with it. Yeah.
So actually, and also in case of this LNG tanks, so we will have the density and the viscosity will be quite different from the water. So what, which type of results, like you expect that, which will be changing? So.
Yeah, so I have not worked on the sloshing with the different density, but I know that one of my colleague used the MLPG because it was developed in collaboration with the City University. So they use this different viscosity as well as different density, and they have done it for Lloyd's. That's what I remember. So they did for different density and viscosity, and then in the MLPG, and then they reported some results, but I don't know what was the outcome of it. Yeah.
Okay, thank you. And also you had shown a very nice that twin body shape, you know, in the, that is, I think, is it for the catamaran type of hull problem?
Yeah, so actually that is just a test case. We did a simple test case in our glass flume, okay. To validate our numerical model. So we have just taken a general dimension. It's not exactly equal to a catamaran dimension as such. Okay, but of course it is, we have done we want to have a numerical experimental result to compare our numerical model. So for that, we just take two hulls and then we did in our lab.
So you mean that instead of the square rectangular section, if we go for ship shape section, then
correct.
Also
yeah, you can do it. Yeah. So this is just see, the first part is we want to because all our models we are developing our own schemes. So we want to validate it. So for validation, we want our own experimental results. So for that, we did our own experiment and then we compared it. Now it's others to take it forward to the next part of it.
Oh, thank you for the clarification. And then regarding this overset grid, so can you little bit enlighten us on that? This overset grid.
So overset grid, I'm not. We have not applied any of those overset grid in our models as of now. Okay, because we want to do something different apart from the overset which is available in the star system plus and everywhere it is available, the overset grid. So it's basically a two mesh, to be precise for the layman's sense. It's basically two mesh wherein they try to transfer the information from the one mesh to the other mesh through the schemes, wherein we don't want to go into that particular topic. So that is why we went into the fast fictitious domain, wherein in our case, basically solid will be also solved as a fluid. Okay, so the solid phase will also be solved as a fluid phase, and then at the end of the time step we will enforce the rigid body dynamics over there. Okay, so in that way we really don't need this overset approach wherein the entire solid phase will move along with the Cartesian grid. So that was the advantage with this. But of course, overset is another approach wherein we can do the same approach for the moving bodies, as well as for suppose if there is a towing carriage, the one which I have shown you, the moving cylinder forward speed. So actually we can use a overset grid because you have a Navier-Stokes domain full, and then you have the entire solid object, the region alone can be moved over the Navier-Stokes domain. So that is what they do basically in the overset grid. So that is the advantage of doing it. So that we want to do it in reverse way by modeling a solid also as a fluid. So that is the one which we have done. Yeah, sure.
And one more very interesting problem you had shown is regarding that bank erosion problem in the river Hooghly.
Yeah.
So what is the exact output? Like you give a restriction on the ship speed, or what exactly?
Exactly. So that is one of the interesting work wherein this is part of the sponsorship from. I mean, this is a sponsored project from Sagarmala project through NTC-PWC. So wherein we measured the bank erosion. I mean, we have not. We measured each of the ship which is moving in the Kolkata port. There is a Ulberi area. So we actually track each of the ships. As well as we measured the wave, the wave pattern, and then we also correlated with because it's mostly the sediments is in the Hooghly rivers is driven by tide, okay, rather than the ship wakes. But in some stretches, whenever there is a curved stretch, there are possibility that this may also occur due to the ship wakes. That was our first thought. So we want to investigate that process. So in order to do that, we did some experiments, I mean the field experiments, as well as we did some numerical model work. And then we quantified what is the sediment transport rate due to the tide, and what is the sediment transport rate due to the ship wakes alone, based on the measurement, as well as we try to rerun the entire thing in the numerical model, and then we want to get the quantification. So we found out that during the calm period, that is a neap tide period, we notice the ship wakes are going to be predominant in causing the erosion part of it. And other one which we come out of this particular exercise was that we want to understand the sediment, because most of the PIANG guidelines, of course, they gave based on the ship size, okay, the ship dimensions, they try to give what is a wave height that one would expect, and what is the safe distance between the two ship which is moving. Okay, those are the guidelines which are already available, as well as what is the speed at which it has to move between the two things. So we try to correlate all those things, as well as, but unfortunately for the Hooghly River, any of the existing PIANG as well as US Army Corps, the sediment transport estimate does not match with our experimental field experiments sediment transport rate. So we come up for this Hooghly estuary, we come up with our own empirical formula. So that is we have just now communicated those work. So we come up with our own empirical relationship, which is slightly modifying the coefficients of the PIANG guidelines for the Indian coast for this particular bank. And then we try to say what is a safe speed between the two ship that is moving. So that was the part of the thing which we are. One of the thing is we noticed that there are two waves which will be going to come up. One people call as a primary waves, other one is called as secondary waves when the ship is moving in the confined channel. So the secondary waves, we notice the secondary waves are basically the one which is going to dominate the sediment transport, the bank erosion part. So that was a major conclusion from this particular study. Yeah.
So very good. And finally, is there any, actually, I could not see any questions on the chat. And one last actually questions, you told so much about the numerical application, etc. But never you have mentioned how much is the computing power and what is the scale of the computing resources which you will require for this one. Briefly, if you can explain.
Yeah, sure. Say, I have shown you different models. Say, for example, the potential flow. The FNPT, that is a fully nonlinear potential flow, which is a two-dimensional one. It basically mostly deals only with the waves, the wave kinematics, trying to get the wave kinematics. It's basically, it's hardly take 15 minutes of any normal laptop. If you use a Busnik's model, that is the 2-kilometer one, that also takes an hour, about 2 or 3 hours. And in the case of a particle-based method, it depends upon the number of nodes, that is the size of the domain. Say, for example, if I have a 6 lakh number of nodes, grid points, the node point, it may hardly take, depends upon the simulation duration. Some of the cylinder cases which we did, which was already reported in one of the combined paper wherein I told you different solvers have been used. There we have reported the computational time for each of the solvers of the 20 solvers. So our MLPG solver basically lies for 7 hours for reproducing that particular cylinder case with the fixed cylinder case, only just 7 hours. In the case of a RANS, again, it is a fixed case, it is 7 hours or 8 hours or so. Where in the case of moving cylinder with the more number of mesh, it may take 2 to 3 days. So it depends. That is the computational time which we are looking at. So one of the idea is try to reduce it. That is why we went for this coupling approaches.
So you are using any supercomputing technology for your any?
We are, as of now, our codes. I mean, the RANS 3D is the MPI. But we just use our Aqua cluster, which is just, I mean, normally we will not go more than 10 cores. That's all. Okay, so that is what we have never put it into 300 crores. That's what people will normally do in other simulations that we have not done.
So thank you for your very enlightening and very nice presentation. Actually, for for the benefit of the participants, as Dr. Purnima told, so actually this INA has been organizing this type of seminar nearly every Saturday for the past several months. And then this video, that recorded video of this one is freely available in their website. So even in the later part, if people are interested, we can always download and go through the presentation for maybe, because it's difficult to absorb everything in a one go. So suppose we want to have again a look at it. So it's always possible to download this online seminar from this INA website. And I really thank, because I think after Dr. Mr. Jyotisman Dasgupta, that he has been taking this initiative of calling so much of expert and organizing this session. It's really interesting and a very fresh added to the activity of our INA. So I hope this activity is continued. And also I want that this to be given as much advertisement as possible to all our students, so that the benefit is spread around to more of the students and also the industry. So thank you very much. So thank you, Mr. Dasgupta, that you are organizing this, and I hope you will continue this in the near future for the benefit. It's really very beneficial, and also that you are keeping it recorded in your website and making it freely available. So that's a very big service you are doing. I really want to appreciate your efforts, sir. Thank you very much.
Thank you very much, sir.
Thank you.
The accolades should go to Dr. VBS Iyengar and Mr. Amir Ahmed and the team of INA. they're putting in their best to do, whatever they're doing. I just want to tell one information to Dr. Sriram that I wonder if you have seen the OCDI guidelines from Japan. We have used it instead of Pyang for ship-to-ship interaction during the design of a terminal. And I found that OCDI guidelines is very, very nice, very good, very detailed and good one.
So that is from Japan, is it?
From Japan, yes.
Okay.
Okay.
Sure. Thank you. Thank you.
With that, I thank the panelists and the audience. I think the formal Thanksgiving will be given by Dr. Iyengar. Thank you. Thank you.
Thank you, sir. My thanks to Dr. Jalihal first, the chief guest of today, because she was very prompt that when we just called her almost at the last minute, maybe just 5 or 6 days back, when we just called her and requested her to chair the session and be the chief guest, and she kindly accepted. Same thing goes to Dr. Nagarajan also. One late evening, I just called him and told him 4 days this session can just chair the session. I thank the chief guest in the session. Dr. Sriram we had personally interacted maybe just 2 weeks back. And that was the time they just requested, can you give this elaborate lecture, because he was giving a 15-minute lecture on the topic. So I thought we should do good service to the topic that he was talking. So a longer lecture would be very useful. And he readily agreed that was the time I was just giving the messages to everybody that Dr. Sriram was like, thank you, sir. It was a very enlightening lecture. INA without Mr. Dasgupta's behind support, as well as Amir, none of things would have been organized. Particularly, Amir is taking all late night WhatsApp messages from me to organize these things. Thanks, Amir. And with that, with your permission, sir, we can conclude today's session. As Dr. Nagarajan has told, this is available in the YouTube and INA website. I hope the community will be enlightened by it. Thank you, sir.
Thank you. Thank you very much.
Thank you all. Thank you.